Okay, welcome to Lecture 2, Real Analysis. Last time we, in Lecture 1, started by discussing some preliminary tools that we'll need to construct the real numbers. We started by constructing the rational numbers, and if you recall, the way we did that was we defined sets and relations. And a couple of important relations are equivalence relations. Another idea that you can define using relations is the idea of a function, and we'll say more about that. You'll see more examples of that later. The idea of an equivalence relation is basically a way of grouping together objects in a set that you want to consider as being equivalent. And so when we defined the rational numbers, we defined them as equivalence classes of certain objects. And because this is the way we grew up learning about rationals, those objects are named by these symbols, P over Q, for instance, right? Like 4/5, 1/3. But the way you should think about them formally is as an object that represents a whole class of things. Okay, so the first example of that might be, one example of that might be the class 1/2, which contains a bunch of things in it. What were those things? They were pairs. They were ordered pairs. 1, 2 is an element in this class. But what's another thing in this class? 2, 4. What's another ordered pair in this class? 3, 6. There's a bunch of them. I won't write them all down. Okay? Okay. These all represent the same thing. And of course, you grew up realizing that, or grew up learning fractions this way. You grew up saying, oh, I could call this class 1/2, but I could also call it 2, 4, or 3, 6. These are all names for the same thing. Okay. Okay. So, and what is the equivalence relation? Well, it's just the usual cross ratio that you're used to thinking about. So here, Pn equals Qm is just the cross ratio you get by, this is the way you grew up learning about how to tell if fractions were equivalent. You take you cross multiply 3 times 4 and 2 times 6 and check if they're equal. Okay? Okay, and so this is in fact an equivalence relation which satisfies 3 properties. What are the properties? The reflexive property says that 1/2 better be equivalent to 1/2. Okay. The symmetric property is the second property, and that says what? About, let's say, 2 things that are in this class. 1/2 equals 2/4 and 2/4 equals 1/2. Yeah, if 1/2 and 2/4 are in the same class, then 2/4 and 1/2 are in the same class. Okay, that's a very obvious property you'd want to be true about an equivalence relation. And then the last property says that if a first thing is equivalent to a second thing and a second thing is equivalent to a third, then the first should be equivalent to the third. Okay, very natural properties for an equivalence relation. Okay, so this is where we ended last time. We ended by constructing the rationals as a bunch of classes. Okay, so here's what we want to do today. We want to talk about the arithmetic structure of the rationals. And we want to understand in what sense do the rationals extend the integers. So let's begin. We can begin by thinking a bit about what this means. Let's roll up the boards here. So our plan then is to talk about properties of Q. Q is our symbol for the rational numbers. And in particular, we want to talk about its arithmetic and its order properties. And we'll see that that leads into a discussion of the algebraic structure of Q, which is naturally a field. So the first thing to ask yourself is, what do you mean by addition? And just to set the stage a little bit, let me remind you that all we have right now, as we've defined the rationals, is a bunch of classes, right? So here is the whole universe of rational numbers. And inside this universe are classes of objects. So, you know, there's all these fractions, which I'm writing instead of as ordered pairs, as fractions. Right? There's a whole bunch of these. Etc. Okay? But some of these are equivalent, so we've grouped them in classes. Right? Some of these are equivalent. Oh, these are definitely not equivalent. Some of these are equivalent. Let's make sure my picture says, speaks truth. And these are, of course, equivalent to other things, but there's probably lots of other things in here, right? This is in some class of stuff, right? There's other things in here, but these are classes. Okay, great. So here's the thing we want to do now. We want to talk about addition. How are we going to define addition? So let's take a stab at it. What does it mean to add this class to this class? What would that mean? Well, let's suggest a definition. Here's one possible definition. And I'll just tell you right off the bat, it's a bad one, okay? This is a bad definition, okay? But you tell me what's wrong with this definition. How about, this is probably a very common way to define addition if you're in grade school. This is a way a lot of people get wrong. All right, let's define addition to be add the numerators and the denominators. Okay? You can't stop me from defining addition this way. Okay? Now, what you could do is point out to me why this is not a good definition. Why is this not a good definition, Willie? Okay, what Willie is saying is that this definition has a following problem. Aside from the fact that it seems to be perhaps meaningless, that's another issue, it has a more basic problem. And the more basic problem is it's not what we call well-defined. Okay? So let me just illustrate with an example. If I tell you to add the fraction 1/2 and 1/3 according to this rule, you will get 2/5. Okay? Remember, these are just objects. I'm not associating a meaning to them. I'm just using this rule. But what is 1/2? It's also equivalent to lots of other things, but in particular, it's equivalent to 2/4 according to our definition of rational numbers, right? But what if I now add this to the same fraction, 1/3? What will I get? 3/7. But you can immediately check that even though these two things are in the same class, these two things, the result is what? They are not equivalent according to the equivalence relation. Are you with me? It's a basic problem. You want, anytime you're dealing with an object that's defined in terms of classes, the definitions you use should not depend on the representatives you pick. Okay? Should not depend on the representatives you pick. So another example might be equivalence classes of college students, right? One way to define equivalence relation is to look at all the freshmen, all the sophomores, all the juniors, all the seniors. Class by class, there are 4 classes, and these are equivalence classes, okay? And I want it to be the case that anytime I define something in terms of freshmen, sophomore, juniors, and seniors, that the answer should not depend on the representative chosen, right? Okay. So, for instance, I might ask something about college students. I might ask, how many classes have you taken? Right? There's a question I could ask of a college student, and the answer might depend on which class you're in, but it shouldn't depend on which person you pick in the class. And of course, that particular question is not well defined, is it, for the equivalence classes of college students? Because a freshman might take 8 courses or 10 courses, depending on what, how insane you are. Exactly. Okay. What is a question whose answer is well defined for the classes of students? Freshman, sophomore, junior, senior. It's an example of a question whose answer is well defined. Jenny? What year will you graduate? There seems to be some concern about that. But for the most part, what year you're predicted to graduate has a well-defined answer. Are you with me? Okay. We want the same thing for our definition of rational addition of rationals. Okay. Well, so that's a bad definition. It's not equivalent, and what the message here is the addition is not well defined. This particular addition is not well defined. So just to be very explicit, I'll say what we want. We want a notion of addition that does not depend on the representatives chosen. Does not depend on the representatives of chosen. Okay? And this is what we say when we mean, this is what we mean when we say well-defined. Addition of classes is well-defined. We want addition of the classes to be well-defined. Okay? Okay, so let's suggest another notion. How about this one? Here's another different notion of addition. We might look at, how about this? Let's let A over B plus C over D. I'll define that to be 0 over 1. There's a definition. Is it well defined? How would you check? You're smiling at me, you're smirking at me, because this is not the notion of addition you're used to. But I just want to know, is this notion of addition well defined? I'm adding any pair of fractions, and I always give back the same class. So, does the answer depend on the representatives chosen? No, in fact, the answer doesn't even depend on what classes you pick, right? Which is even another issue. Okay? It's well defined. So this is well defined. You can check. I'll let you check this. It is well defined. But it has a problem, and that is it's meaningless. It's kind of a boring definition, but boring. It's uninteresting. It would be not doing us very much good if this definition didn't have some meaning to us. Okay? Okay, so let's define addition in a meaningful way. So here's the good definition. And this is the one we'll use throughout the rest of this course. A over B plus C over D equals, everybody should know this, good, AD plus BC over BD. Okay, so this is a notion. And by the way, remember, in mathematical communication, more so on your writing of mathematics than on the board work here, but I will try to do it in the board work. Everything should be expressed in a complete sentence or a thought, right? So this is this plus this equals this, right? Equals is the verb, and I'm finishing the thought here with a period. Okay. Notice I've tried to do that here and here as well. Okay. Okay, very good. So this is the definition. What would I have to do, and you're going to do this on your homework, what would I have to do to show this is well defined? To show that it's well defined, I want to do what? I must show what? Okay, good. So two members from the same equivalence class will give you the same answer. There are lots of course, several classes we're talking about, so I might change the representative here. I might change the representative here as well. And I want to know, is the answer going to be in the same equivalence class when I do that? So how do I say that mathematically? So mathematically, we will, here's what you want to verify on your homework. So to show that it's well defined, I must show the following. If AB is equivalent to A prime B prime, and what? CD is equivalent to C prime D prime, then what? Yeah, that's right. AD plus BC, comma, BD is equivalent to A prime D prime plus B prime C prime, B prime, comma, B prime D prime, period. This is continuing this sentence. I must show this. So this is our goal, okay? So in your homework, you want to start off with these statements. And, of course, then that will yield a certain relation, right? You take the cross multiply and get a certain property of that A prime, B prime must satisfy. Similarly for here, and you want to work through the consequences to show that these are in fact equivalent. Okay? So that's one of your homework assignments. It's tedious, but it's good to do such an exercise at least once in your life. Okay, so you know what foundations you rest on. Okay, that's addition. What about multiplication? Well, by now, of course, you know that we're trying to create arithmetic with some meaning, and you've already learned some of the meaning of multiplication. So it makes sense to do this the way you learned in grade school. So if I want to multiply two fractions, I'll define this to be what? AC over BD, the class of, right? Okay. And again, I want you to check that this is well defined. Also on your homework. Again, that means you're going to have to convert this statement into a statement about pairs. Okay, ordered pairs. Okay, good. We have an arithmetic, and it's good news that it does, in fact, the addition and multiplication are well defined, and there's a reason for that. It's because it has a physical meaning, right? The one you grew up learning. Okay? But now we've defined rationals in terms of integers, just integers. But I want to know, in what sense does this new construction extend the integers? And so here's a question then. How does Q extend Z So in what sense does Q extend Z? Well, the first thing you have to tell me is which elements of Q correspond to a particular integer, the integer 5. What class of fractions is equivalent to 5 as an integer? 5, 1. 5 over 1. Good. So here's one thing you want to say then is 5 over 1 corresponds to 5. N over 1 corresponds to n. And that correspondence would be kind of uninteresting if it weren't also for the fact that the arithmetic also extends, right? So what you want to check is, you want to check that the set of all classes n over 1, where n is an integer, you want to check that this behaves like Z does. Behaves as Z. Okay, this is an informal way of saying that this subset of the rationals is isomorphic to Z. If you've taken algebra, some of you have taken 171, we're just talking about isomorphism. If you haven't, don't worry about it. Okay. But you want to check that, in fact, that this correspondence here, n over 1, corresponds to n. So the correspondence, so make this a sentence, I'll say the correspondence is this, period. And you can check that, in fact, if you add n over 1 plus m over 1, you get n plus m over 1. And if you multiply n over 1 times m over 1, you get nm over 1. Okay? These are the things you would check. Very easy to do. Okay? So, what do we have now? We have a picture that's no longer looking like this, but now somehow has a structure that tells me how I can add certain elements, multiply elements, and some special classes of these happen to behave just like the integers do. Okay? That's good news. Now what? Well, okay, I have this thing, Q, that extends the integers, but the integers also have another property. What's another feature of the integers? Yeah, there's an ordering of the integers. Okay? So Z has an order. So I have to talk about what an order relation is, and we want to know, does Q have an order as well? And of course, you grew up learning about what the order might be, but let's just think carefully about how we might define such an order. So, help me out here. I want to define a notion of order that would be consistent with the kind of order, the ordering we think of for integers. 2 is less than 5, and minus 7 is less than minus 3. First of all, what is an order? I'll give you a hint. It takes two things in, and it describes some kind of relation between the two. So what is an order?
It's a relation.
It's a relation. Good. And what property should it satisfy? So an order on a set S is a relation. And we usually write it, not surprisingly, by a little caret. Okay? It's a relation we'll call less than. We'll use that symbol, satisfying some properties. What properties should an order relation satisfy? I'll give you a hint. There are two properties it must satisfy. Jenny. What do you mean by anti-symmetric? Ooh, interesting. Okay. Yeah, so that's actually very closely related to the property I'm about to write down. There's one other thing that could be true. A is less than B, B is less than A, but those are not the only things. What else could be true? Steve? They could be equal. So we'll call this the law of trichotomy. So the law of trichotomy says that exactly one of these things is true. So if X and Y are in the set S, exactly one of these is true. Okay, I haven't left myself enough space here, but the three things are X less than Y, X equals Y, Y less than X. Okay, that's the first property. And what's the second property? What do you think should be true, Emil? Transitivity, I've heard that word before. What does it mean? Good. So we'll call this transitivity. And you've seen this before, but I'll write it down. If X, Y, and Z are in S, then, and if X is less than Y and Y is less than Z, then X is less than Z. These are two properties. And just to make sure that this is a sentence, this should probably be a comma or maybe a semicolon, because I've just finished saying one thing and I have another property here. And two. Properties 1 and 2, period. Okay. Okay, good. If you have an order on S, then you call S an ordered set. So here's another way to say the same thing. An order on a set S is relation. So if you have this, we'll call S an ordered set. If it has an order. Okay. Okay, very good. So what is the ordering on Z? So here's an example. In Z, and in the integers, what's an order? Ooh, okay. A is less than B if B minus A is positive. I like that, but what is positive?
Greater than 0.
What is great? But greater depends on an order. Okay, so you define order in terms of positive and positive in terms of order, and we want to avoid that, but that was a nice try. But you have the right definition, so we just have to decide what positive means. What is positive? What does it mean for an integer to be positive? Tell me your name. Keith. Okay, we haven't defined absolute value, but and you guys are, I know you're trying to define positive in terms of other things, but why not just say what positive is? What is positive? Which is? What's C plus? Good, let's just write down a set, okay? So in Z, we're going to say an integer. We'll say, okay, I'll write this. M is less than N if N minus M is positive. That's correct definition. And what positive means is, i.e. just means, in other words, in the set 1, 2, 3, 4, 5, ... Okay, we'll just declare those creatures to be the positive ones. Okay, you can't stop me from doing that. Okay, just try. Just try. Okay, here we go. Good. So this is Z. This is what we mean by positive, and this is what we mean by one is less than the other. How do you think we're going to do this in Q? How do you think we're going to do this in Q? By the way, there are many other notions of order you could consider, right? I mean, we just gave one, but there are lots of other ways to order the integers. And you might enjoy thinking about how you might do that. You're going to explore some notions of order on your homework, not this week's homework, but next week's homework. There's a notion of dictionary order, so maybe I'll just do this as an example. In Z cross Z, these are ordered pairs of integers. We can declare AB to be less than CD if something is true. Well, let's see. So the dictionary order says, first you check the first element, and then you check the second. Okay, so we'll say that AB is less than CD if A is less than C, or if A equals C and B is less than D. So if one of these conditions is true, and this is a notion of an order. It's called the dictionary order for obvious reasons. Everybody with me? I guess this is not a sentence, it's just a statement about what we call this order. Bonnie?
Would that work as an order for the complex number?
Ooh, excellent question. Well, how would we answer that question? We don't know what the complex numbers are yet, but for those who perhaps do, would this dictionary order work for the complex numbers? Well, first of all, does it satisfy this trichotomy relation? Sure. Is it transitive? No? What would keep it from being transitive? You're just checking dictionary order. There's no reason it's not transitive, right? So it would work for the complex numbers as well. I mean, if you're thinking complex numbers as pairs of reals, right? So in fact, your homework asked you to think about this. Okay, it's an order. Okay, good. What about Q then? What will we say about Q? How will I define an order on the rationals? Well, how about doing something very similar? So we're going to say m over n is positive if so by similar we probably should say what we mean by positive. And then we'll say one fraction is less than another fraction if this one minus this one is positive. So how can we define positive? Yes?
Oh, sorry, I had a question before. We defined addition, but we didn't define subtraction or negative yet. So do we know how to subtract two rational numbers?
Oh, yes, excellent question. The question was, do we know how to subtract two rational numbers? We will define subtraction as adding the negative of, where negative is multiplying by minus 1. And so we know how to multiply two rationals. And we will associate to minus 1 the rational minus 1 over 1 and perform the multiplication that way. Yeah, I won't do that out, but we'll assume we're going to do that in the natural way. So in particular, what that means is anytime you have a rational, if you want to subtract two rationals, that's the same as adding minus c over d, and just treat minus c as an integer. We know how to multiply negative numbers that are integers. Okay, excellent question. So how would you help me define a fraction as being positive? Just use your intuition. Yes, tell me your name.
Drew.
Dhruv.
We can say m times n, the integers m times n, and then use the definition we used for z.
Okay. So look at mn and ask, and say this is positive if mn what?
If mn is positive.
Good. This is another way of saying positive because mn minus 0 is in that set. Okay? But we know what this means for z already. Okay, great. There is a little bit of a concern here, though, that we didn't have when we're talking about the integers. We just made a definition involving the rationals. We've just made a definition. What's one thing you should worry about when you make a definition about a bunch of equivalence classes? Good. You should train yourself to thinking. If I have some object that's a bunch of equivalence classes, is it well defined? And I'll let you check this. It's a well-defined definition. We'll do this without writing it. What do I have to do to check that it's well-defined? Well, you give me another fraction that's in the same equivalence class. Let's say p over q. If m times n is bigger than 0, is p times q bigger than 0? Well, we know Pn equals Qm. That's the condition. And if m times n is bigger than 0, you can check that p times q will in fact be bigger than 0. Involves a little bit of work, but check that you can do it. Okay? These are some of the things you might do when you go home and review the notes to check your understanding. It is well defined. Okay, good. And then say mn is bigger than less than m prime n prime if m prime over n prime minus m over n is positive. Positive. Sorry, I gotta do this here. Okay, good. So we're being very careful at first to define these rationals, but once we have these these properties, we'll just start using them without worrying about going back to ordered pairs. Let me mention, we sometimes write this symbol, y is bigger than x. That's the symbol we use for x less than y. I'm already using the words less than and greater than to think about these symbols because they come from our notion of order that we've grown up with. And we'll also write, sometimes we'll write x less than or equal to y. Notice the line below the less than symbol to mean, what does this mean? Okay, or x is less than y, or x equals y. Law of trichotomy would make it equivalent to what you just suggested. Okay, very good. So we've just defined what we mean by order on Q. Okay, so stepping back from what may appear to be a little bit tedious, but we're being careful here because we're building the foundations. We no longer have this picture, do we? Now there's a way to think about the rationals the same way we think about the integers. We think about the integers as ordered, living on some kind of line, perhaps, where this is to the left of this if this is less than this. Right? So the rationals actually live on such a line as well. So let's think a little bit about what that looks like. So a new picture of Q. We can think about it as here are the integers. Let's use some different colors here for fun. Right? 0, 1, 2, minus 1, minus 2. We have this notion of order, and there are some rationals here, and you can check that, for instance, 1/2 is less than 1, so it belongs here. And it's bigger than 0. 1/4 is between these two in the order, etc. Right? 5/4 minus 1/2, etc. minus 4/3. Okay? And there are a lot of more points here as well. Yes, don't make me write them all down. But there are a lot of them, and we'll answer the question of exactly how many there are in a few lectures. Okay? Okay, so we have a new picture, and guess what? This picture is good enough to answer some questions. Right? So Q, in some sense, is good enough to solve some questions we might be wondering about. So, for instance, if I have 3 cakes and I want to divide them among 5 people, I might be interested in equal shares for everybody. And so 3 cakes have to satisfy 5 people equally. Then I'm interested in the answer in solving this equation, right? Is there an integer that solves this equation? No. Is there a fraction? Yeah. In fact, it's clear what that fraction is because of the rule I just erased, right? The multiplication rule. Cross multiplication, we can see that x equals 3/5 satisfies this equation, solves this. Why? This is 5. It's the same as 5/1 times 3/5, and these multiply, and you get 15/5, which is equivalent to 3/1, which is 3. Right? This is just the arithmetic you learned in grade school. Okay? But it's on firm foundations now. Now, from here on out, what I want you to do, unless you're asked a problem that is actually foundational, you can just assume that we know the properties of the rationals. I'm not going to ask you to go back to working with ordered pairs. Just work with fractions as you're used to. Okay? So we have the rationals, and they're good enough to answer some things, but they're not good enough to solve all equations of this form. Here is another example. What about x squared equals 2? Claim it's not good enough to answer this question. And let's, in fact, see why. I will do that above. So some of you have seen this proof before, perhaps in discrete mathematics, but I want to do it for the benefit of everyone who has not seen it. And you have a homework that's very similar, but in some ways different. So this may elucidate some points you hadn't thought about before. So this is a fact that we will prove as a theorem. There is no solution. X squared equals 2 has no solution in Q. Another way of saying it is, this is the way you've often heard it said, is square root of 2 is not rational. Okay, and I'm avoiding saying that here because we haven't defined the square root of 2. Okay? All I'm saying is, in the rationals, there's no solution. So, here's a proof. It's a classic proof by contradiction. And if you're going to do a proof by contradiction, it is customary in mathematical writing to tell the reader you're about to do a proof by contradiction, by writing proof and then parentheses by contradiction. Now, you'll notice I've put a period here. This is not a complete sentence, but this is convention. This is just customary mathematical writing. Okay, so it's okay to do this. Okay. Proof by contradiction. Okay, so what is a proof by contradiction? Well, the way a proof by contradiction normally goes, you start off by assuming that the thing you're trying to prove is false and show that leads to a problem. And if it leads to a problem, then the thing you started with, which is the opposite of what you're trying to prove, couldn't have been false, so it had to be true. Okay, that's sort of the basic plan. So let's just illustrate with this example. X squared equals 2 has no solution. What is the, if this is not true, then what statement would I be starting with? Good. Assume that there is a solution in Q, has a solution in Q. Okay. This is the way to start. And now I will change this statement into to a more formal statement, i.e., let's say x equals p over q. Are you with me? What else should I remind the reader of about p and q if I'm talking about fractions? Good. Where p and q are in Z. Okay. The shorthand equals and the shorthand contained in, these are generally acceptable for mathematical writing, even writing on a piece of paper. Okay. Okay, very good. Now, I claim there's one more thing I might want to assume here, but it's not going to be obvious to us off the bat that I'm going to need this. Okay, so what I want you to do is leave a little space and assume that something else is true. Something else is true. Okay? But just to motivate how you might begin this problem yourself, you might not be able to see what's coming. Okay. So if you're solving this problem yourself, you'll start by contradiction because now you actually have something concrete to work with. X equals p over q. So what does that mean? Well, that means that p over q squared equals 2. Right? With me? Okay. We know how to work with fractions. We can assume all the arithmetic properties that we've talked about before. So this means, and another way to say that is hence. What does this mean? What is p over q squared? P squared over q squared. And if I use cross multiplication, what do we get? P squared equals 2q squared. In mathematical writing, you have to know something about your reader, but we're assuming your reader knows how to work with integers and fractions. And so making the jump from here to here is probably okay. The reader can probably reproduce this argument, right? So you don't need to show all the steps if you assume your reader understands what you're doing. Okay? Okay, good. P squared equals 2q squared. So what can I conclude about the number p? It's even because it is divisible by 2. Then p is even. And I'll say it this way because this might be a better way of thinking about it. It's divisible by 2. Why is p even? There's a little bit of a jump here. Yes? Excellent question. The question was, are we going to say first that p squared is even? And the answer actually depends on, a little bit on, whether you think that's an important fact. Okay? Some of you made the jump here very quickly. But I claim it's actually a little bit of a jump that you might want to help the reader with. Okay? So, remind me your name? Maya. Maya is suggesting we should tell the reader that there's an intermediate step, and I agree with this. The first step is to notice that if something equals twice something else, it's that something that you're noticing is even. P squared is even, correct? Now, how do we make the jump from that to the fact that P is even? Yes?
We know how integers work, and I assume we know how integers work, and we know that two even numbers multiplied by each other will produce another even number, and two odd numbers won't.
Okay. Yeah, so, I mean, if you want, you could go all the way back to unique factorization of integers into primes, etc. And it's helpful to think about that if you really want to. But another way to say it is then P is even. And here's one way to justify it. You might say because if it were odd, if P were odd, P squared would be odd. Or another way to say it is if P had a factor of 2, P squared would have a factor of 2, right? If P squared had a factor of 2, okay, then P would have to have a factor of 2 as well. Okay, then P is even. Good. Now, what does this mean? So I can write P as what? If it's even. It's twice something. I like M because the letters M and N are often thought of as integers. But if P equals 2M, what does that imply? Hence, P squared equals 4M squared. And what does that imply? 4M squared equals what? 2Q squared. Yes, question. Ooh, excellent. Yes. These are all good things. In fact, the process of doing a proof, you often realize things that you need to add later. And so this is a good example of something to clarify your writing. In fact, this would not be a very good proof if we didn't say that. So thank you for pointing that out. So we should probably insert here where M, for some M and Z. For some M in Z. Thank you. Hence, P squared equals 4M squared, and 4M squared equals 2Q squared. Okay, we're almost there. What does this mean? We feel like we're going somewhere, I think. If not, this is at least what you would do to play around with the problem to get a feeling for what's happening. But what does this mean? 4M squared equals 2Q squared. Then 2M squared equals Q squared. Okay, then this kind of looks like something we've seen before. What can we say about Q? Then Q is, okay, now we maybe should tell the reader first that Q squared is even, hence Q is even. You've made this argument once, you probably don't have to make it again up there, okay? I feel like I'm going in circles. P is even, Q is even. Haven't reached a contradiction yet. What could I do?
Make the assumption that P and Q have no common factors, and then if they're both even, they have the common factor of 2, and we do have a contradiction.
Now why would I want, first of all, why is that true? Why can I assume that P and Q have no common factors? Because what? Okay, yeah, if they did have common factors, you know because of the equivalence of fractions that you could make it equivalent to one that didn't by canceling the common factors. So assume that P and Q are in, we say, lowest terms. This is the key ingredient we need. In other words, have no common factors, i.e. have no common factors. Here's where we're really using the fact that we can pick whatever representative we want. We might as well pick a good one. And then this would give us a contradiction. Then this contradicts the fact that P and Q are in lowest terms. Okay, so what does this mean? This means that the assumption that x squared had a solution yielded a logical impossibility, a contradiction. Therefore, what? So, x squared equals 2 must have no solution in Q. Okay. Now, when you get more sophisticated, you're going to assume the reader understands when you do a proof by contradiction, you're just trying to get a contradiction and you're ending the proof there. But at least for the first few weeks of this course, you should probably remind the reader that you've reached the contradiction. Okay. Later on, you may not need to write this as much, but try to do it at first just to get in the habit of thinking about the reader. The way we'll think about this course, by the way, is each time you're writing a proof, think about writing the proof for a person who is 2 weeks behind you in this course. Okay? So there are things they don't know that you know, and you want to emphasize the important points. Often we end our proofs with a symbol. Books do this. Or you can sometimes use the letters QED. Books also do that as well. Okay? Okay, very good. So we have the rationals. They have an order. They have an arithmetic. They're good enough to solve some equations, but not others. And in order to try to figure out what it is that that characterizes the rationals, we'll have to talk about some properties they satisfy. So, last thing I want to talk about today is that Q has an algebraic structure. It's called a field. Okay. So what does it mean for Q to be a field? Well, you can check that the rationals satisfy a bunch of properties, and anytime you have rationals that satisfy a bunch of properties, these properties, it's called a field. Okay, these are all in your book, so I'm not going to write them all down. But the idea is a field is a set with two operations. The operations are traditionally denoted by plus and times, and you'll notice there are 5 properties for addition that mimic the 5 properties for multiplication. Okay? Closed, you'll see the actual definition in your book. Property being closed means if you add 2 things, you're still in the set. Okay? Commutative means A plus B equals B plus A. Associative means you can group in any collection you want. If you do A plus B first and then add C, it's the same as if you add A to B plus C. The additive identity is what leaves a particular element unchanged. A plus a 0 element is A. An additive inverse means that there's something you can add to a particular element A to get the identity. Okay? Multiplication, exactly the same properties, except possibly which one? Yeah, M5, that axiom is slightly different. You have to worry about the 0 element. And finally, addition and multiplication should intermesh in some way. What way should they intermesh? Well, a multiplication should distribute over addition. So, for the rationals, what are the identity elements? additive and multiplicative? So the 0 element is what? What behaves like 0? What ordered pair behaves like 0? 0, 1. Very good. The class of 0, 1. Actually, yeah, so it's not just this. It's the class 0, 1. Okay? Which consists of a bunch of representatives. The multiplicative identity is what? Yeah, 1 over 1. Okay? And you can check all these properties. Check these axioms hold. Okay, and you know enough to do that now. You'd have to go to basically back to ordered pairs and check them, but you can check that they do. Now, this is a structure which occurs in many places, and particularly later we'll see the real numbers also are a field. Okay? Are the integers a field? What properties do the integers not satisfy? Why are the integers not a field? Good. Z is not a field because it does not satisfy what? M5 in particular. Jenny. Oh, yes. Sorry. Thank you. This should say, if you're watching at home, on your slide, M5, the last line should say, every element except 0 has a multiplicative inverse. Thank you. That is a typo. Okay, so Q is a field. And the other thing that's very interesting about Q is that not only is it a field, it's an ordered field. Q is an ordered field. And despite what the name implies, an ordered field is not just a set that is both a field and has an order. What else would you like to be true about an ordered field besides the fact that it's an ordered set that is a field? What else would you like to be true? I'll give you a hint. Let's see. We have this other structure that has two operations, and that's nice. That's fine, except the operations should somehow play with each other, right? Nicely. And they do with distribution. Okay, that's what with a field, you have these set with these two operations that play together nicely. Okay, here is now a set that has these two structures. It's got an order, and it's a field. What else would you hope to be true? That the order and the field properties do what? Play nicely. Okay, good. So it's an ordered field. So what is that? It's a field with an order. So that, well, how would you like the order and the field properties to play nice with each other? What would you suggest? There are two operations to a field. Maybe I want to know how they relate to the ordering. For instance, so that two things are true. Well, here the way to say it is the order is preserved, in some sense, by the field operations. Okay, and I'm going to put this in quotes and then tell you what I really mean, which is if y is less than z, this implies that what happens if I add x to both sides? How do you think x plus y and x plus z should relate? Less than x plus z. That's the first property, comma. And the second property is if y is less than z and x is bigger than 0, second property should say how multiplication relates. This should imply that what? xy is less than xz. Notice that we are demanding that the thing you multiply be positive. Okay? I'll mention that this is slightly different than what's written in your book. Your book has, I'll call this 2 prime. Your book has a condition that is slightly different but equivalent. And I encourage you to read what the book says and see why it's equivalent. Okay, but this is the way I like to think about it because it makes it very clear you're trying to have the order be preserved by the field operations. Okay, just got to be careful about positive factors here. Okay. Okay. So, what do we have now? We have Q being an ordered field, which is basically says something about its structure. Okay, so here's where we're heading now. We're heading towards constructing the real numbers. And our hope is that maybe, so this will be next time. Our hope is that maybe the real numbers, whatever they are, might be good enough to solve the algebraic equation x squared equals 2, as well as other things. And hopefully they will also somehow contain the rationals. So in some sense, they extend the rationals. So they'll extend the rationals in some sense. So Q. And what else will they do? Well, they will also have not only will they have the property that they'll solve equations like x squared equals 2, but they will in some sense fill in the holes in the line, the number line that we began to get a picture of. So it will be also an ordered field, but it will have a property that we'll call complete. So it'll be what's called a complete ordered field. Okay, so it will live on a line, like a number line, but it won't have the holes that the rationals do. The rationals don't solve the equation x squared equals 2, even though we know that's the length. That's the length of a hypotenuse of a triangle with 2 sides that are unit length. Okay, so that's next time. That's lecture 3, which will be on Friday. Okay, have a great day.